Hey there, it's Shannon Math Chick Myers, and today we'll take a look at integrals involving the secant and tangent functions, maybe the secant function alone, tangent function alone, etc., etc. Fun times. Ready? If the secant portion of the integrand has an even positive integer as a power, and the tangent portion has any other exponent, then we save two secant factors and convert the rest to tangent factors. Then expand and integrate. The angles must match. All right, so here we go. We've got the secant function, the angles are, and the tangent function. The angles are the same. The secant function is even. So we're going to go ahead, and the tangent function has any other exponent. It doesn't matter. So we're going to go ahead and rewrite this bad boy as secant squared at x times tangent at x cubed, the quantity cubed. And then this other portion we're going to hang out for, because at the end of the day our g of x is going to be tangent at x, so we're going to need a secant squared at x dx for our g prime. You see the evil plan? Mwahaha. All right. And then next up, we're going to convert secant squared at x, that first factor, into tangents. So we'll get tangent squared at x plus 1, or vice versa. And then times tangent at x, the quantity cubed, times secant squared at x times dx. This will be, now is when I distribute. So I'm going to separate it into two integrals. So we're going to have our tangent function raised to what power? Awesome, the fifth power. And we have this secant squared at x times dx going with it. And then plus the integral of tangent at x, that quantity cubed, times secant squared at x dx. And so in this case, our g at x is tangent at x. So g prime at x is secant squared at x times dx. And you've got that for both of them. So then we'll use that general power rule. So we're going to get 1/6 times tangent at x to the, all of that to the 6, plus 1/4 times tangent at x to the 4th, plus our constant of integration. And we're good to go. Groovy? All right. So now, and I'll just highlight just to make sure you've got it, our g prime of x was all of this here. That's why we were able to use that general power rule. All right, so next up, what if you've got the secant and tangent functions, but this time, in this situation, the secant portion of the integrand has an odd positive integer. Sorry, there's a typo here. And the tangent portion has an odd positive exponent. So both of them are odd. Then we save one secant tangent factor. And because our evil plan on this one is to have g of x be the secant function, and that's its derivative, right? And convert the rest to secant factors. using the fact that tangent squared at some angle A is equal to secant squared at that angle A minus 1. That's just manipulating the Pythagorean identity around. And then we expand and integrate. Again, those angles have to match. If you have a definite integral, you can find the indefinite integral first and then back substitute. All right, so find the definite integral. Here we go. Both of them are odd. So we will have secant at x squared times tangent squared at x times secant at x times tangent at x dx. Good so far? Equals integral. I want to keep my secant factors. I'm turning that tangent squared at x into secant squared at x minus 1. And then secant at x times tangent at x dx is my g prime. So g at x is going to be equal to secant at x. G prime at x is going to be secant at x tangent at x dx, which we have. Groovy? Okay, continuing, we have, so now I'm going to multiply through. So I'm multiplying on the left by secant at x, the quantity squared, and you still have that third factor, secant x, tangent x dx. Whoops, and I forgot my x, I'm sorry. Okay, so here we go. I'll split the integral again. We'll have secant at x to the 4th power times secant at x tangent at x dx minus the integral of secant at x, the quantity squared, times secant at x times tangent at x dx. And so our g prime is ready to go. We're set up to use that general power rule now. So we'll get 1/5 times secant at x to that 5th power minus 1/3 times secant at x to the cube plus our constant of integration. And we're all done. Good, good? All right. Now, what if we've got the tangent function raised to an even positive integer? So, if there is only the tangent function in the integrand, which has an even positive integer as a power, we rewrite as the product of one tangent squared factor times the remaining tangent factors. Note that the second factor will be a positive even integer. Then we convert the tangent squared factor using the fact that tangent squared at some angle A equals secant squared at that angle A minus 1, and then we expand and integrate. Again, when you're evaluating definite integrals, you can find that indefinite integral first and then back substitute. So let's do this. We've got the tangent function alone. It is raised to an even positive power. So this will equal 2. So this one's a little weird. Our our g of x is actually going to end up being tangent at x. We're reserving that tangent squared at x factor so we can convert it into secants. And so our g so we have a secant squared factor, which is the derivative of the tangent function. So g prime of x will be secant squared at x dx. So let's do it. We've got the integral of tangent at x to the fourth times tangent squared at x with respect to x. This will be, so this one's got quite a few lines. This will be equal to the integral of, I'm going to put this tangent like this so we know we're going to want to use that power rule. We're going to change this guy to secant squared at x minus 1. It's actually not that long. And then we will have the integral of tangent at x to the fourth times secant squared at x dx minus the integral, I'm splitting into two integrals, of tangent at x to the fourth dx. So the first one is good to go. Do you see that? Now we're going to have to work for it a bit. So this one's good to go. We can integrate this one. So we'll do so. This will be 1/5 times tangent to the fifth at that angle x. Now this next one, we're going to have to use the same kind of plan. You rewrite it as tangent squared at x times tangent squared at x dx. So you're applying the same rule again. So this guy goes along for the ride. And this should look familiar. Okay, so now I'm going to split this into two integrals. We'll have the integral of tangent at x, quantity squared, times secant squared, at x dx. And then when I distribute through, it's minus and minus, so we get plus. And then we'll just have the integral tangent squared at x dx. So now we can evaluate that second integral, or now it's the first integral, that second term. That's going to be 1/3 times tangent cubed at x. And again, here's it's that same g prime. And now, well, we got to change this in terms of secant squared at x minus 1 dx. So if you need to split the integral, you can. I'll show it by splitting the integral. We get the secant squared at x dx, and then minus the integral of 1 dx. And finally, we can finish. I know these probably seem a bit intimidating. So hopefully your trig identities and your algebra is getting to be very, very seasoned again. So the antiderivative of secant squared at x dx is just tangent at x. And then minus x plus our constant of integration, and we are good to go. Groovy? Awesome. Hang in there. You got this. All right, so now we're going into integrals involving the tangent function raised to an odd positive integer. So if there's only the tangent function in the integrand, which has an odd positive integer as a power, we rewrite as the product of one tangent factor times the remaining tangent factors. Note that the second factor will be a positive even integer. Then we convert the tangent factor, which is raised to the positive even, sorry, not poser, power, into secant factors using the fact that tangent squared at some angle A equals secant squared at that angle A minus 1. And then expand and integrate. Note that on some of the terms you'll be reserving a secant tangent factor to be able to integrate. And then again, if you're evaluating a definite integral, you can find the indefinite integral first and then back substitute. So here we go. We've got tangent at x raised to the 5th power. So we can go ahead and write this as tangent to the 4th at x times tangent at x dx. And then we want to basically rewrite the other tangent, the tangent raised to the higher power in terms of the secant function. So evil plan, some of them you're going to have g of x equal to secant at x. So if we think of this as tangent squared at x squared times tangent at x dx, then we can start turning this into secant factors. So here we go. We will have secant squared at x minus 1, the quantity squared, times tangent x dx. And then expanding that square, we'll have secant squared to the 4th, at x minus 2 secant squared at x's plus 1 times tangent at x dx. Now we're going to multiply through tangent at x dx to each term and see what we have and split those integrals. So we'll have secant to the 4th at x times tangent at x dx minus 2 times the integral of secant squared at x times tangent at x dx, and then plus the integral of tangent at x dx. Good so far? Now the trick is, if you have your g of x equal to secant at x, you need a secant x tangent x, right? So if g was equal to secant at x, g prime at x is equal to secant at x times tangent at x. And sorry, I meant to write that as g at x. So here we go. We have the integral of secant at x, the quantity cubed, times secant at x tangent at x dx minus 2 times integral secant at x to the 1 power times secant at x times tangent at x times dx. And then this one has an antiderivative formula. That's negative natural log absolute cosine at x. So we'll have 1/4 times that secant function to the 4th power, and the angle is x, minus 2 times 1/2 the secant at x squared, right? And then minus our natural log absolute cosine at x plus c. Cleaning it up a bit, we'll have 1/4 times secant at x to the 4th minus secant squared at x minus natural log absolute cosine at x plus our constant of integration. Groovy? All right, here we go. If you've got just the secant function raised to an even positive power, we rewrite as the product of one secant squared factor times the remaining secant factors. Note that the other secant factors, note that the second factor will be a positive even integer. Then we leave the secant squared factor alone and convert the other secant factors into tangent factors using the fact that secant squared at some angle A is equal to 1 plus tangent squared at that angle A. Then we expand and integrate. Groovy? Okay, so here we go. We've got the secant function alone and it's even. So we rewrite this as secant squared at x times secant squared at x times dx. Now we'll convert the one of the secant squared factors into tangent and reserve the other one. So we'll have 1 plus tangent squared at x times secant squared at x times dx. So noticing that if we end up with a g of x at tangent at x, our g prime at x is secant squared at x dx. And now we multiply through, so, and I'm going to split the integral. So we'll have secant squared at x dx plus the integral of the tangent function squared times secant squared at x dx. So notice you have your g prime as needed on the second one. And this is one of those so easy it's hard things. The antiderivative of the secant function is just the secant squared at x is just the tangent function. So then we'll get plus 1/3 the tangent cubed at x plus our constant of integration. Good, good? Awesome! All right, now this one, this next one can get very mean. I'll show you the very first one where you'd have secant cubed at x dx or some angle. Basically, if there's only the secant function in the integrand and it has an odd positive integer as a power, we have to use integration by parts, where at the end we combine like integrals. So we let u equal to secant at x, or I'm going to just say a so it's more general, and our dv equals the rest of the factors times dx. And remember, the formula for integration by parts is the integral of u times dv is equal to u times v minus the integral of v du. Then you combine like integrals. If the original odd power is greater than 3, you'll need to keep using integration by parts until you no longer have an integral in the result. When evaluating definite integrals, find the indefinite integral first and back substitute. All right, so here we go. We're going to rewrite this bad boy as secant at x times secant squared at x dx. And so u equals secant at x, du is secant at x times tangent at x dx. And then our dv, we just have a secant squared left, right? So dv would be secant squared at x dx. So v is tangent at x. All right, so I'm going to rewrite the original one since we're going to be equating like integrals. So secant cubed at x dx equals. So we have our u, which was secant at x, times our v, which is tangent at x, minus the integral of v and then du. Cool so far? Okay, so now we're going to have to do a little more work here. So inside that integral, do you see that we've got 2 tangent factors, and then we have the 1 secant factor, and then times dx. So we'll switch those tangent factors into secants, or into secant squared minus 1. So you basically simplify that integral and rewrite it in terms of secants again, and you might have multiple integrals. So this will be secant squared at x minus 1 times secant at x times dx. Continuing, we will have, almost there, we'll split the integral, so we're at that expand portion of the show here. So we'll have minus the integral of secant cubed at x dx, minus a minus is plus, and then we'll have the integral of secant at x dx. So we're adding a secant cubed at x dx to both sides. Like integrals, integral secant cubed at x dx. So then on the left-hand side, we'll have 2 of the integral secant cubed at x dx's. On this side, it zeroes out. We're left with secant at x times tangent at x. And then the antiderivative of secant at x with respect to x is natural log absolute secant at x plus tangent at x. So again, another so easy it's hard one. And then we can call it adding C1. We're going to divide by 2. So we'll have the integral of secant squared at x dx is equal to 1/2 times secant at x times tangent at x plus the natural log of absolute secant at x plus tangent at x. And then we'll just call this plus c. A constant times 1/2 is just another constant. Awesome. All right, so this is the last little bit of this portion of the section. If you like what I'm doing, go ahead and hit that like button, share the video, subscribe to my channel, whatever you want to do. And I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. Bye.